Hello, Honors Biology. I just wanted to thank you for being so willing to work this weekend while I'm recovering. So, you've done quite a lot so far this week with learning about the cell membrane and how the membrane allows some things to be transported and some things to not be transported. And we're going to go over these things. I do promise you that. So if you're still confused by some things, one thing I would ask is if you could write them down. If you could go through your notes and put little question marks or underline what still is confusing, and that would greatly help both of us know what we need to go over. I heard good reports today. You guys did a really nice job with the lab, so I do appreciate that. And I'm looking at the data right here, and I'm seeing that we got some pretty consistent results. Now, normally this lab, I would have every group do all 5 solutions, just to ease the details to help with the sub and just to make our lives a little bit easier. I only gave you guys one solution, but I did pull up some data from last year, and you can see down at the bottom some of the numbers, and I'd like to include these in our average. It's always nice to get more data. So, one thing I'd like you to take note on, and this is what happens every year. Some students will get, and this is exactly what should happen. I don't want anybody to be alarmed. Some people get very positive numbers. Some people get right around 0. And then the rest are somewhere around negative numbers, and they get more negative. Notice -2, -9, and then I don't know who this group is. If they could fill that in, that'd be great. We got a little bit of aberrancy here. I would just ask maybe for period 5 that maybe you go back over your data and just double check that you calculated things correctly. But hey, these things happen. It's really, welcome to working with living organisms. Sometimes they don't behave correctly. -1.8, -2, -2.1. -2, -4.9, -5.4. So notice we've got some things going on here, kind of interesting. So one thing I would point out is all of these results are dependent upon this formula, the percent change. And we use percent change because if you noticed, or if you think about it, not everybody's potato had the same mass to start out with. And so just like if we were tracking people's heights and how much they grew over middle school, well, if somebody starts at 5'5" and somebody else starts at 5 foot, you would have to put that into the formula at some point. Because if the 5.5 person only grew an inch and got to 5.6, so here's our 5.5, only grew an inch to 5'6", but then another person who's 5 foot grows to 5.5 5'5", excuse me. Well, clearly this person grew more, but you wouldn't know it from the absolute values. So we use percent change to give a relative amount. And so you can see that relatively that 4% had bigger numbers, and then the 0% also had big numbers. Now, where does the positive and negative come in? Well, the positive and negative comes in because if the final amount is bigger than the initial, well, notice this is a bigger number then. So we got a final minus initial. This is going to give you a positive number. That means that in the 0% at least, our potatoes gained, I can't write here, there we go, gained mass. Now, where is that mass coming from? But water. Water entered the potato cell. Now, the 1% is rather interesting because we've got one group that had no change, one group gained about 1%, one group gained 0.9%, one group last year lost a little tiny bit, and then another group had nothing. So this is an interesting one. I want you guys to be thinking about that. because what that implies is the final and initial were pretty close to each other. And then 2%, 3%, 4% salt all had negative numbers. Now, negative number means that the final mass is less than the initial, which means the potato lost mass. Now, if somebody in the first class, feel free to average the numbers, and once you get your average numbers, what you're going to graph the average percent change with the solution percentage. So let me set up the graph for you. Now this graph is going to be kind of interesting because you're going to use the negative quadrants, and we've not had a graph do this before. So your y-axis is going to be your percent change, and of course we're going to use our average. And go ahead and use the data from last year as well, because it's nice to be able to share and collate as much data as possible. The law of large numbers, right? And then our x-axis is going to be your salt solution. And so we'd have 0, 1, 2, 3, 4. Now, some of these numbers are going to be large and positive, like this first one, 0. And I can even see this is going to be somewhere around 4-ish, something like that. And so you're going to go above the x-axis. But notice real quickly, we're going to get down to close to 0. I don't know what that is. You guys can figure that out. But everything else is going to be negative. So negative, negative, negative in some way. So you're going to get a line that's going to cross the x-axis and go downward. Now we're going to do what's called a best fit line. So a best fit line means that even if some of your dots are not perfectly in line, you want to see if you can eyeball a line that fits it. So let's say my data looks like that. A best fit line kind of just figures out where the line should go, where you've got 2 points slightly above and 2 points slightly below, and you're trying to fit that line. There's a fancy mathematical way that you could do this called a regression line. If some of you know how to do it, then knock yourself out. But you can also eyeball it and do a line of best fit. Because this is a pretty linear relationship. How much water goes in. Now let me give you some thoughts about this. In the distilled water, notice we would have all water. It's 100% water. And then we have our potato slice in here. There's my potato slice. Now the potato slice has some solutes. It has some salt in it. So there's our sodium chloride, my little dots, sodium chloride. And of course, they actually separate out. So some of it's sodium, some of it's chlorine. But the water outside has nothing. So what you always want to consider is the concentration of water. Now, by default, if you have any solutes in the solution, it's not 100% water. Now, don't worry for now. I'm just pulling a number out of my brain just to get us thinking about this. Let's say, for the sake of argument, this is 98% water and 2% salt. Well, that means the water is lower on the inside of the potato. This is low concentration of water. The 100% water on the outside is high. Water is going to diffuse into the potato, and that makes it gain mass, and that makes it positive. Now, what you want to be thinking about is, if it gained mass, then what kind of solution is this? Is this a hypotonic? Is this a hypertonic? Or is this an isotonic? Okay. And then for your the negative solution, the negative solutions, and I'll just leave it here right now. We don't have to go through all of them, but here's our potato slice, and we know just from looking at our numbers that in all of the ones that are below the x-axis, they lost water. Remember, because final minus initial over initial, if they lost mass, that means their final is lower than the initial. They lost water. So we know water left to go to the solution outside. And again, I want you to think, is this a hypotonic? Is this an isotonic? Or is this a hypertonic? Now, if you wait, we'll kind of cover that. And then here's an interesting matter. What about this point on the graph where it crosses the x-axis? That means the percent change was 0. And think about that mathematically. If the percent change equals 0, that means your final mass equaled the initial mass. That means the potato doesn't gain or lose. And hopefully with the virtual labs, you saw that there is only one kind of solution that does not gain or lose mass, and that's the one where there's an equal amount of water going out and in. So let's recap. In the 100% distilled, we know that water goes overwhelmingly into the potato. A little tiny bit goes out, but overwhelmingly goes in. There's one that is equal where it crosses the x-axis, and then all of these where the water goes out of the potato. So what I would like you to do for class today is graph in your lab book a graph like this. And of course, it should be scaled. I'm missing my scales. I'm missing a title. I'm missing my numbers here. But of course, you'll do a better job. And so I would like you to do the scales. I would like you to draw a picture like this that I have that shows a little bit neater where the water is moving. And then I would like you to I'd like you to try to figure out where does it cross the x-axis? So let's go ahead and finish this up. And like I said, if you're still not, I get it. If this is still confusing, please jot down, okay, I somewhat get this, but could you go over that in your notes? If it gains water, this is a hypotonic solution. If you were thinking that, then yay, good job. The solution that neither gains nor loses is an isotonic solution, where the solution outside is equal to the solution inside. And then the solution that loses water is a hypertonic solution. Now, I don't need any conclusion for this lab. I'm trying to cut ourselves a little bit of a break. But I do want you to do a really good job with this graph. And I would like you to identify the types of solutions. Remember, anything that gained mass is a hypotonic solution. Anything that stays the same is an isotonic. And anything that loses is a hypertonic solution. So hopefully that helped direct ourselves a little bit for today. And please do jot down any questions you have. And make note of that in your notes so that when we do come back together again, I can help you in the best way possible. Miss y'all, and we'll look forward to seeing you Monday. Bye.